This section is on linear inequalities, but before we actually get to linear inequalities, let's quickly review the inequality symbols. We have the greater than symbol, so like 5 is greater than 3, 4 is greater than 3. And then we have the greater than or equal to symbol, and that's the greater than symbol with a line underneath. So 5 is greater than or equal to 3, 4 is greater than or equal to 3, but then 3 is also greater than or equal to 3. We have the less than symbol, so 1 is less than 3, 2 is less than 3, and then we have the less than or equal to symbol. So 1 is less than or equal to 3, 2 is less than or equal to 3, and then 3 is less than or equal to 3. So linear inequalities, these are similar to linear equations, except our graph is a line plus a shaded region. So linear equations were just lines, but linear inequalities will have a shading in addition to the line. So for greater than and greater than or equal to, we are going to shade above the line. For less than and less than or equal to, we are going to shade below the line. For greater than or equal to and less than or equal to, the line is going to be solid. And then for greater than and for less than, the line is going to be dashed. So the solid line is going to represent that the line itself is part of the solution, whereas a dashed line, the line itself is technically not part of the solution. So every point xy that lies in the shaded region works in the original inequality. The graph for each linear inequality is shown. Are the given points solutions to the inequality? So we have the inequality y is greater than or equal to negative 2x plus 6 graphed here, and because it was greater than or equal to, it is a solid line and it's shaded above. So any point that is in the shaded region or on the line is a solution. So negative 5, negative 3 is not a solution because it's not in the shaded region. 1, 4 is on the line, and because it's a solid line, this counts. So yes. And then is 8, 2 a solution? Yes, because it's inside the shaded region. So we can confirm this algebraically if we plug it back into the original inequality. So it should be consistent with the original inequality. And you don't have to do this, but it's kind of nice to see. So let's plug in the first point, negative 5, negative 3. So x is negative 5, y is negative 3. So negative 3 is greater than or equal to negative 2 times negative 5 plus 6. And this will get you 16. Is that true? Is negative 3 greater than or equal to 16? No, that's not true. And that's consistent with what we said right here. So now let's plug in 1, 4. And we get 4 is greater than or equal to 4. Yes, that is true, and that is consistent with what we found here. And then finally, is 8, 2 a solution? We said yes. If we plug that in, we get 2 is greater than or equal to negative 10, which, yes, that is true, and that is consistent with what we found. So again, you don't need to plug it in to confirm, but you can if you want to. So question number 2 is the same inequality, except for this is strictly greater than. It's not greater than or equal to. So the graph is basically the same, except for it's a dashed line now instead of a solid line. So is -5, -3 a solution? Nope. Is 1, 4 a solution? Again, 1, 4 is on the line. But because it's a dashed line, no, it's not a solution. And then is 8, 2 a solution? Yes, it's in the shaded region, so it is a solution.